Hello linear algebra students. In this video lesson we continue our discussion on vectors. Now find two 3D vectors that are perpendicular to both of the 3D vectors below. In our last lesson we learned that two 3D vectors are perpendicular to each other if their dot product is 0. So let's begin with an unknown vector. We'll call it x, with components a, b, and c. To find a vector x that is perpendicular to both u and v, then we need the dot product of x with u to be 0, and we need the dot product of x with v to be 0. This sets up the following. U dot x is equal to, multiplying corresponding entries, we have 3a plus 1 times b minus 1 times c. And we need this dot product to be 0. Furthermore, we need v dot x to be 0. And v dot x would give us negative 2a, no b's, plus 2c, and this dot product must also be 0, so that x will be perpendicular to v. This creates a system of two linear equations with three unknowns. We will solve it using matrices. Convert to an augmented matrix, and then put this matrix in reduced row echelon form, which we will do by hand. I will do one copy of row 2 and add that to row 1. That will put a 1 in the top left corner. Now we will do 2 times the first row temporarily and add that to the second row to replace the second row. Now I will do 1/2 of row 2. And finally, we want this position to be 0 to be in reduced row echelon form, so I will do negative 1 times row 2 and add it back to row 1 to change row 1. And now we have reduced row echelon form for this matrix. The columns were the coefficients of a, b, and c. We can see that there are leading ones here and here, so in the a and b columns, meaning that c is free. So the first row tells us that a minus c must be 0. In other words, that a must be equal to c. And the second row says that b plus 2c must be 0. So in other words, b must be the opposite of twice c. And c is free. This means our solutions have the following structure. A has to be c, b has to be negative 2c, and c can be whatever it wants. Well, we could factor this c out, and that leaves us with c times the vector 1, negative 2, 1. Suggesting that there are infinitely many answers where c is free, and any multiple of this vector, 1, negative 2, 1, is going to be a vector that is perpendicular to the two given vectors. Now that should make sense to you, that if you have a vector that's perpendicular to two other vectors, then changing its magnitude without changing its direction will result in vectors that are still perpendicular to the two given vectors. So two specific examples, for example, of c is 1. Here's one choice of a vector. Or we could let c be some other number like 2, and give this as an answer for a specific vector that is perpendicular to both u and v. Let's look at this with technology. Using CalcPlot 3D, I have graphed both of the given vectors u and v. V is the green vector, and u is the blue vector. Now let's enter our answer, or at least one of our answers. We found that 1, negative 2, and 1 is a perpendicular vector. Let's make it red, and then rotate this image around a little bit. So that red vector, it makes a right angle with the blue vector, also makes a right angle with the green vector. It's perpendicular to both. And now that we have an answer, we found a vector that's perpendicular to both the green and the blue vectors, it makes sense that any multiple of this red vector, so make it a little bit longer or a little bit shorter, or even reverse its direction and have it go this way, it would produce a whole collection of possible vectors that are going to be perpendicular to the green and blue. Okay, let's go to the next page. The cross product of two 3D vectors that are not scalar multiples of each other produces another 3D vector that is perpendicular to both vectors and is calculated in the following way. So when you are working with three-dimensional vectors, we have another way that we can find a vector that's perpendicular to two given vectors, and it's called the cross product. So right here we have something called u cross v, and these have to be 3D vectors for this to be defined. So here's our three-dimensional vector cross another three-dimensional vector. And it's calculated by doing the determinant of the following 3×3 matrix. In the first row, we put the standard basis vectors I, j, k in the first row. In the second row, we place the coordinates of the vector of the first vector you see here, so the u vector. And in the third row, we put the coordinates or the components of the second vector in the cross product. That goes in the bottom row. And then notice that we have these absolute value bars. That means we calculate the determinant of this 3 by 3 matrix. Let's go ahead and do this for the following pairings. So here's the vectors u and v. Notice these are the same two vectors from the previous page. We're going to see what the cross product produces for us. So u cross v will be equal to the determinant. I'm going to put vector I, vector j, and vector k in the first row, then go the components of vector u, and then the components of vector v. Now to calculate this determinant, I'm going to do cofactor expansion along the first row. So we'll target the I first. That I is in a positive position with regards to the matrix of signs. So we have a positive vector I times, and then we multiply the 2 by 2 determinant of the submatrix that's not currently crossed out. So 1, negative 1, 0, 2. And then we move our targeting to the j vector. This is in the negative position with regards to the matrix of signs. So it'll be minus the j vector times, and then the 2 by 2 submatrix is 3, negative 1, negative 2, 2. And then finally, we move our targeting to the k. And this is back into a positive position. So we do positive k vector times, and then the 2 by 2 submatrix not crossed out. And we calculate all these 2 by 2 determinants. In the first case, we get 2. So we have 2 times I, times the vector I. This 2 by 2 determinant will be 6 minus 2 will give me 4. But don't forget we have the minus sign in front of the j, so this will wind up being minus 4 times vector j. And the final 2 by 2 determinant will be 0 minus negative 2, so 2. So we'll get plus 2 times vector k. So back into other vector notations, this would tell us that the vector 2, negative 4, 2 is a vector that is perpendicular to both u and v. Now you'll notice, if we go back to our previous slide, that all multiples of this vector right here are going to be perpendicular to the given u and v. One such vector is the second one we put up here in our notes, the vector 2, negative 4, 2. I leave it to you to verify, but if you were to take these same two vectors and do the cross product in the reverse order, that this would give you the opposite sign of the result of doing the cross product in the first order, in the original order. In other words, it should give you negative 2, 4, negative 2. Which is a vector pointing in the other direction, but still perpendicular to both u and v. Okay, now let's study the cross product of these two vectors, a and b. Let's go in this order, a cross b. First row is ijk. Then we put the components of a next, and then the components of b at the bottom. So we do vector I times the determinant of this 2 by 2, which will be negative 2 minus negative 2, which will be 0. And then minus vector j times the determinant of this 2 by 2 submatrix, which would be negative 6 minus negative 6, which would also give us 0. And then finally, plus vector k times the determinant of this 2 by 2 matrix, which would be 6 minus 6, so also 0. So in this case, we get the 0 vector. Now you might notice that in this case, vector b is simply a multiple of vector a. In fact, in this case, it's twice of vector a. That's twice the magnitude, but the same direction. Whenever you do a cross product of two vectors where one is simply a multiple of the other, you should get the 0 vector back. This is why up here, we say that the cross product of two 3D vectors that are not scalar multiples of each other will, in that case, produce another 3D vector that is perpendicular to both of the vectors in the cross product. Looking at technology, we have the two vectors given, a and b, and you'll notice that they both point, in this case, in the exact same direction. In such a case, when the vectors are pointing in the same direction, just they have different magnitudes, the cross product will produce a 0. Also, if they point in opposite directions, so maybe this blue one is pointing in the opposite direction out this way, but would still be a scalar multiple of the green vector, it would simply be a negative scalar multiple of the green vector, and even in that case, the cross product will be 0. Okay, let's go to the next page. An n-dimensional vector has n components. So we're now going to venture into dimensions more than 3. Once we get to 4th dimension and higher, it becomes a challenge to visualize what is happening, because our limited brains allow us to think really only in 3 spatial dimensions. But we can still perform mathematical operations with vectors that have multiple dimensions. And sometimes you have a multiple dimensional vector where the dimensions aren't necessarily spatial dimensions. Like maybe a vector will have 4 components, where one component is temperature, one component is x spatial direction, one component is y spatial direction, and maybe another component is time. And so you can still say that this is a 4-dimensional vector where only 2 of the components are spatial dimensions, and the other 2 are different kinds of quantities. Regardless, a n-dimensional vector has n components. What those components stand for is another story. Now, many of the concepts pertaining to 2D and 3D vectors generalize to n-dimensional vectors. Given the 2 5-dimensional vectors below, calculate the vectors that follow. So m is a 5-dimensional vector. If you want to do the opposite of m, then you simply distribute the negative through all the components. So change the sign of all components. So we'll have -3 instead of 3, +1 instead of -1, -1 instead of +1, 0 doesn't change sign, so it stays 0, and that 5 will become -5. And this is how we would calculate the opposite of the vector m. If we do 1/2 of the vector n, then simply distribute the 1/2 through all the components. So 2 times 1/2 is 1, 3 times 1/2 is 3/2, or 1.5, 0 times 1/2 is still 0, 4 times 1/2 is 2, and -2 times 1/2 is -1. We create this vector that is 1/2 of the vector n. N minus m is done still component-wise, just like it was for 2D and 3D vectors. So we would take the n component, so do 2 minus the m component. Make sure you go in that order. So we do 2 minus 3, get -1. And then we do 3 minus -1, so that's 3 plus 1 gives us 4. And then we do 0 minus 1 will be -1. Then 4 minus 0 will be 4. And finally, -2 minus 5 will be -7. And 3m plus 2n, I'll go ahead and do this in 2 steps. So let's triple m first. That gives me the vector 9, -3, 3, 0, 15. And to this we'll add the vector double n. That will be 4, 6, 0, 8, -4. And then add these component-wise. So we'll do 9 plus 4 is 13, -3 plus 6 is 3, 3 plus 0 is 3, 0 plus 8 is 8, and 15 plus -4 is 11. Okay, let's go to the next page. Again, many of the concepts pertaining to 2D and 3D vectors generalize to n-dimensional vectors, including the statements below. So if you have 2 n-dimensional vectors, u and v, then we can still perform a dot product, which is also called an inner product. Sometimes mathematicians will reserve the word dot product for 2 and 3-dimensional vectors, and they'll switch to the word inner product when we're talking about 4-dimension or higher. But for our purposes, we'll accept the terms dot product and inner product as synonymous or interchangeable. Also, you can find the magnitude of a vector v by square rooting its dot product with itself, which winds up giving just the square root of the sum of the squares of the components. Okay, find the magnitudes of each 4D vector below and find their inner product. Let's begin with vector A here, find its magnitude. The magnitude of vector A will be the square root of, and then we square the components and add them together. So 2 squared is 4, -1 squared is +1, 0 squared is 0, and 5 squared is 25. And in the end, this gives us the square root of 30. The magnitude of B will be equal to the square root of, square -1 is +1, square the 4 is 16, square the 1 is also +1, and square the 2 is 4. And this gives us the square root of 22. And now let's find their inner product. A inner product with B, or A dot product B, or simply A dot B, will be equal to, and this will produce a scalar as well. We multiply corresponding entries and add the results. So 2 times -1 is -2, -1 times 4 is -4, 0 times 1 is 0, so I'll put plus 0 there, and 5 times 2 is 10. Adding these results, we get 4. 2 n-dimensional vectors are orthogonal if and only if their inner product is 0. Now in the case of 2D and 3D, we use the word perpendicular, But in general, we can use the word orthogonal whenever a dot or inner product is equal to 0. However, if we're working with 4-dimension or higher, and we can't visualize the vectors, then it loses meaning to say that two 4-dimensional vectors are perpendicular to each other, but we can instead switch to the more general word orthogonal and say that two 4-dimensional vectors can be orthogonal if and only if their dot product is 0. Now, in this case above, for A and B, since the dot product of A and B was 4, it was non-zero, this tells us that the vectors A and B are not orthogonal. If the dot product had been 0, then we would say they were orthogonal to each other. And finally on this page, scale each 4D vector above to a unit vector. The process we discussed for 2D and 3D vectors applies to any dimensional vector. We can make its magnitude be equal to 1 by scaling it appropriately, and that scale factor will be 1 over the magnitude of the vector times the vector itself. So in the case of vector A above, it'd be 1 over radical 30 times the vector A, which you could rewrite by distributing the 1 over radical 30 to each component. So 2 over radical 30, negative 1 over radical 30, 0 over radical 30 is still 0, and then 5 over radical 30. This is a 4-dimensional vector that we're going to say has the same direction as vector A, but now has a magnitude of only 1. So it is a unit vector. We can do the same thing for the vector B. 1 over the magnitude of vector B times vector B itself, and I'll go ahead and do all this work in one step. The magnitude of vector B was radical 22, so basically divide every entry of B by radical 22, giving us negative 1 over radical 22, 4 over radical 22, 1 over radical 22, and finally 2 over radical 22. And we have a 4-dimensional vector that has a magnitude of 1, but points in the same quote-unquote direction as the vector B. Okay, let's go to the next page. Complete each statement below and verify for specific cases. Identify which statements apply to which dimensions. Now, the dot or the inner product can be applied to any dimensional vector, but it only makes sense to do a n-dimensional vector dot with another n-dimensional vector. So 4-dimensional dotted with another 4-dimensional. You would not want to do a 4-dimensional dotted with a 3-dimensional. However, the cross product operation is limited to 3-dimensional vectors only. So looking at all the statements here, every single one that involves a cross product must only be involving 3D. So all of these statements right here are 3D only. Okay, the first one. What we want to establish with this first statement is that when you dot two vectors, it doesn't matter the order in which you dot them. When you think about the mathematics behind calculating a dot product, you multiply corresponding entries and add the results. The ordering of the two factors for any one product doesn't matter. The second statement says if you have a scalar times a vector and you dot it with another vector, you can instead factor the scalar out and dot the two vectors first. An example of something like this would be, let's do a 2-dimensional case. Let's say we had the vector 2, 4, and I'm going to dot it with the vector negative 1, 3. Well, the first vector, we can essentially recognize it as twice the vector 1, 2. So I can factor out a 2 of that first vector, and then do the dot product of these two vectors first. So that would give me 2 times, and then dot producting these vectors, we multiply these entries, and then add the product of those entries. So this would be negative 1 plus 6, which is 5, and then double that, we get 10. This is what you would get if you calculated the dot product of the originals. 2 times negative 1 is negative 2, 4 times 3 is 12, and negative 2 plus 12 is going to be 10 still. If you have a sum of vectors and then you dot that with another vector, the dot product effectively distributes. So you would have u dot w and then add v dot w. We can demonstrate this with this example right here by decomposing the vector on the left. Let's say the vector on the left is decomposed into a sum of two other vectors. And let's just pick those vectors might be, let's say 3 and 2, and then the other one would have to be negative 1 and 2. So I'm imagining two vectors that when you add them together, make this vector. And then I'm going to dot this with the vector negative 1, 3. And use this distributive property. So we get the vector 3, 2, dotted with the vector negative 1, 3, and then plus, and then we're going to dot negative 1, 2 with the vector negative 1, 3. And this gives me negative 3 plus 6. So we get 3 for the first dot product, plus, and the other dot product will be positive 1 plus 6, which is 7. And sure enough, we get 10 again. Now when you dot a vector with itself, we discussed this in the last lecture, you wind up getting the sum of the squares of its components, which is its magnitude squared. Now let's do some properties with the cross product. The cross product is not commutative. If you switch the order, you get the opposite sign. So if you do switch the order, you need a negative sign to be produced. So negative v cross u. The dot product is commutative, the cross product is not. If you have a constant times a vector u, and you cross that with a vector v, you can also factor that constant out and just do u cross v first. I'll leave it you to verify this. A vector cross with itself will always give you the 0 vector. So combined with the previous statement, a vector cross with a multiple of itself, for example, if there was a k here in front of this u, you could factor that k out and do the cross product of u and get 0, and then k times the 0 vector is still the 0 vector. So a vector cross itself or a vector cross a multiple of itself will, in both cases, give you the 0 vector. A sum of vectors cross product with the vector w also will distribute. So we'll get u cross w. Just make sure you write u first, then w. And then plus the vector v, write that first, and then cross with w. Here you have to be a little bit more careful. You have to put the w's second because the w was second here. And the cross product is not commutative. If you cross product a sum but from the left side, then it will also distribute, but this time you would keep the w's on as the first vector in each cross product. And then finally, this last property, if you have a cross product, keep in mind this will produce a 3D vector, and we're assuming this one's also 3D in this case, and then you could do the dot product of the two 3Ds, and this will produce a scalar in the end. Turns out in this case that you can do the following instead. You can do u and dot product it with, and then cross v and w. Again, v cross w will give you a 3D vector. U is also, we'll assume, is a 3D vector, and then when you dot product them, you'll get a scalar. And this property is saying that you can do this you could do this one of two different ways and get the same scalar. Let's go ahead and verify this last one for some specific cases. So I've just chosen 3 different 3-dimensional vectors, and let's do this side first. We'll cross u and v and then dot it with w. So u cross v will be the determinant of this 3x3 matrix. Targeting the I first, we have I, vector I times 6 minus negative 1, that's going to be 7, minus vector j times, and now I'm focused on the determinant of this 2x2, which will be 3 minus 0, or just 3, plus vector k times, and now focusing on this 2x2, we have negative 1 minus 0, which is just negative 1. So this basically gives me the vector 7, negative 3, negative 1. And now let's dot this with w. So we're going to multiply these entries and get 14, then multiply these entries and get negative 3, and then multiply these entries and get negative 2. And combining these results, we get a 9. Okay, now let's do this side of the identity by beginning with v cross w. So v cross w will be the determinant of this 3x3 matrix. Using cofactor expansion, we get vector I times the determinant of this 2x2, which is negative 2 minus 3, which is negative 5, minus vector j times the determinant of this 2x2 matrix, which will be 0 minus 6, so negative 6, and then plus vector k times the determinant of this 2x2 matrix, which will be 0 minus negative 2, which is 2. So this gives me the vector negative 5, positive 6, positive 2. Now let's dot this result with the vector u. So I'm going to multiply the first component of vector u with this first component of v cross w and get negative 5. And then we'll do 2 times 6, which is 12, and then 1 times 2, which is 2. So we had negative 5 plus 12 plus 2, which also gives me 9. Okay, let's go to the next page. For any two n-dimensional vectors, u and v, the following inequalities hold true. So let's begin with this one on the left, called the Cauchy-Schwarz inequality. Now, in the 2 and 3D case, we did learn that when you dot product two vectors, you get equal to the magnitude of one vector times the magnitude of the other vector times the cosine of the angle between them. It turns out that this statement is also true Turns out this statement is also true for dimensions that are greater than 3. It's just how to interpret the theta that gets tricky. Now, if I find the absolute value of both sides, the dot product is a scalar, so we'll have the absolute value of their dot product. The absolute value of these magnitudes has no effect, so they just stay magnitudes. Remember, a magnitude is a non-negative value to begin with, but this cosine of theta goes inside absolute value. And the cosine of theta will only toggle between -1 and 1 and all entries in between. It's a cosine wave that has a range from -1 to 1. So when you put it in absolute value, you will never get a value more than 1. Thus, it creates an inequality for this statement. The dot product of two vectors will always be less than or equal to the product of their magnitudes. And it turns out this is true for any n-dimensional vector. Now ask yourself, is it possible for the left side and right side of this inequality to be the same value? In other words, when will both sides be equal? Well, in the case of 2 and 3D vectors, where theta is the angle between the vectors, you can ask yourself, when is it true that the absolute value of cosine theta is actually equal to 1, as opposed to being smaller than 1? If you can determine the angles theta, where the cosine of theta and absolute value will give you 1, then that should tell you those situations where the absolute value of the dot product will be equal to the product of the magnitudes of the vectors. Now, the triangle inequality, we're going to explain it in a two-dimensional context, which you can easily generalize to a three-dimensional context, and then it turns out that it's true no matter the dimension. But in a two-dimensional context, if you have two vectors, let's say we have vector u and some vector v that points in a slightly different direction, and you add them together. So put the tail of v at the head of u, and then their sum vector would be this vector right here. Now with any triangle, the length of any one side is always less than the sum of the lengths of the other two sides. So let me remove the labels for u and v. Imagine the vector v is rotated down so it's pointing, has the same length but not pointing in the same direction as u. And then if you were to rotate u plus v down, it would not be as long. Thus the length of u plus v has to be less than the sum of the lengths of u and v separately. And this is called the triangle inequality. And in magnitude notation, it looks like this. The magnitude of u plus v, which is the green magnitude, has to be less than the magnitude of u plus the magnitude of v. Ask yourself what must be true about u and v so that when you added them together, you get a vector that's as long as the sum of the magnitudes of u and v separately. As you think through this, think about two-dimensional cases. Verify each statement above using the 3D vectors below. All right, let's begin with the Cauchy-Schwarz inequality. Let's find the magnitude of each vector separately. So the magnitude of vector u will be equal to the square root of, and then square the components. So we have 9 plus 1 plus 1, and we get radical 11. Now we'll find the magnitude of the vector v will be the square root of 4 plus 0 plus 4, so we get radical 8. Now let's do their dot product. U dot v will give us a scalar, and that scalar will be 3 times -2 is -6, plus 1 times 0 is 0, and then plus -1 times 2 is -2, and that gives me -8. Now the Cauchy-Schwarz inequality says if you take the absolute value of u dot v, that's the absolute value of -8, that'll be 8, that this should in fact be less than or equal to the product of the magnitudes. So we're trying to determine whether this is a true statement. We get 8 when we calculate just the absolute value of the dot product, and we get radical 88 if we multiply the two magnitudes. And the square root of 88 is a number that's more than 9, because 9 squared is 81. So clearly it's true that 8 is less than or equal to the radical 88. We verified the Cauchy-Schwarz inequality. Now let's do the triangle inequality. So I need to add the vectors together to get a new vector. So adding the components, we get 3 plus -2, get 1. 1 plus 0 is also 1, and -1 plus 2 is also 1. And if we do the magnitude of this vector, we get radical 1 squared plus 1 squared plus 1 squared, we get radical 3. And so according to the triangle inequality, the magnitude of the sum should be less than or equal to the sum of the magnitudes. So the magnitude of u was radical 11, and the magnitude of v was radical 8. Now, is this a true statement? Well, radical 3 is less than 2, and radical 11 all by itself is more than 3, so we can certainly see that this is a true statement. Okay, on to the next page. Suppose two n-dimensional vectors u and v are not scalar multiples of each other. So in this picture here, we see u and v in a 2D context. They're not pointing in the same or opposite direction, so they're not scalar multiples of each other. Then u can be decomposed into a sum of orthogonal vectors a and b, such that a is a scalar multiple of v. This vector a is called the projection of u onto v and can be found as follows. Now, before we talk about this formula, let's talk visually about what we're trying to accomplish. I'm trying to express u as a sum of two vectors that are orthogonal to each other, where one of the vectors is a scalar multiple of v. One of my vectors is limited to being somewhere along this trajectory. And I want to add to it a perpendicular vector. So I'm trying to find these two vectors here, where the green one is in the same direction as v, and the red one is perpendicular to the green one. But we want it so that when they add together, we get the vector u. So the vectors we're after are these red and green ones in this picture, where the green one is a multiple of the vector v. Keep in mind it's possible that v had pointed off this direction to begin with, in which case the green would be a negative multiple of v, so that can happen. But in this case, it looks like the green vector will be a positive multiple of v. And then the red vector is perpendicular to the green vector, and then when you add green and the red together, you get the vector u. So we're going to call the vector a here is going to be some sort of multiple of vector v, and this will be vector b. Now I do want to show you where this formula comes from briefly. So we're going to begin by doing u dot v, and we're going to decompose u into the sum of vectors a and b, and we'll do the dot product of the sum with the vector v. And then our properties from above suggest that the dot product basically distributes here, so we have vector a dot product vector v plus vector b dot product vector v. Now we know that vector b and vector v have to be perpendicular, so this dot product will be 0. And we know that a is some constant times the vector v. The properties of a scalar multiplying by a vector and then doing a dot product is we can factor that scalar to the front and just do the vector v dot itself, and then solve this equation for k. So I'm going to divide this to the other side, to this side over here. And that gives me that scalar constant has to be vector u dot vector v divided by vector v dot with itself, which sometimes it's written this way, u dot v over, and we've learned on the previous slides that a vector dot itself is its magnitude squared. So sometimes you see the formula written this way, where down here you see magnitude of vector v squared. So this k expression is right here, and you can see that a is equal to k times the vector v. So a is a multiple of vector v, meaning it's pointing in the same or opposite direction as vector v. And then sometimes you'll see this notation. This stands for the projection of the vector u onto the vector v, which means that we're after the vector a that you see in the image on the left. Okay, let's go ahead and give the components of u and v based off the imagery here. Vector u is 3 to the right and then 4 up. So its components would be 3, 4. Vector v is 2 units to the right and 1 unit up. So its components will be 2, 1. So vector a will be equal to u dot v, will be 3 times 2, which is 6, plus 4 times 1, so 6 plus 4. And we get 10. Then you do v dot with itself, so we get 2 times 2 plus 1 times 1, so 4 plus 1, we get 5. And this scalar will be multiplied by vector v. So 10 over 5 becomes 2, and we multiply that to vector v, whose components are 2, 1. And so we get, in the end, the vector 4, 2. Now, once you find vector a, finding vector b is easy, because we know that vector a plus vector b needs to be equal to vector u. And since we know vector a, we can say that vector b, therefore, has to be the difference of vector u minus vector a. So vector b will be equal to vector u, which is 3, 4, and subtract from it the vector we just found, which is 4, 2. And this gives us the vector negative 1, 2, which you can see in this imagery, vector b would be left 1, up 2, whereas vector a is right 4, up 2. This process of decomposing u into two vectors, where one of the vectors is parallel to another given vector, and where the two vectors, the green and the red ones, are perpendicular to each other or orthogonal to each other, generalizes to any dimension. It's just that for 4 dimension and higher, having an accompanying visual becomes complicated. And this wraps up our second lesson on vectors.